Okay. Can you guys just go and check, see on the YouTube? Can you see?
Yes, I see. It's unmuted.
Okay.
Let me check.
Can see, right?
Yes, I can see.
Okay. Why we have to on camera? It makes me more nervous. Other groups, everyone switch on their camera, right?
Yeah, they switch on their camera. So
Okay.
should we?
I think we should lah.
Okay.
Yeah. Later lah, later. Around 9:57 we on.
Oh, okay.
Yeah.
Why live is not going on this?
What?
I can't see.
You can't see?
Yeah. What?
Oops. Now can see?
Just the slide that we live just now.
Oh, okay. Why ah? That means our voice we cannot hear lah.
You look in YouTube, you can see now the things that
Wait,
we
wait. Let
see
me
now.
try ah. Wait.
So just see the things that we tried just now. 4 minutes, right?
Oh. Yeah. Why ah? Wait. Oh my god. Why is it like this?
This is because just now we
But I already delete that streaming, right?
okay, I saw it. Okay.
Okay. You can see
Mm,
already?
yeah. Sure.
Okay. But we need to. Okay. We stop the live first. Wait. Eh? How do you see our live? What I see is what we presented before.
You go to you go to your channel.
Okay.
You go to your channel, then you see your icon.
Oh,
The
the first
first one.
one. Okay.
Yeah. Go to your channel, then you see your
Oh,
icon.
okay.
The first one.
Okay. I think we should tell in the group lah so that they know.
Same thing like.
But they can see right the live one, right?
Yeah, I'm right now seeing the live.
Okay. Then okay. Guys, come, let's on our camera. Hello, you guys there?
Yeah.
Okay, I'll on first lah.
Yeah, guys. Yeah.
On camera.
Hi.
Can
Hi. Wait.
Hi.
Hi.
Sorry.
Hi.
Hello, hello. We have 5 viewers. Okay. I think we can start. It's 10:01 now.
How many viewers? Or we can wait, or we
Yeah.
should.
I think Madam is also here. Then there's one. Okay. Okay, we'll just wait for a couple of minutes.
Yeah.
Then we'll start.
Guys, I can't see it live or not because
Uh, Go to my channel and then click on the live video.
yeah. Okay. Got it.
Okay.
Thank you.
Okay, so we'll start in a minute at 10:05.
Okay, so we'll start in a minute.
Okay, I think we can start. Okay.
Okay. Can you all hear me?
Yeah, everyone please off your mics, okay? And we can hear you, okay?
Okay, hello everyone. Welcome to our presentation today. Today, we are going to present about the topic acid and base. Before that, I would like to introduce myself first. My name is Phoebe and my group members which are Hatika, Nathani, Ibrahim, and Hakimi. Today, I'm going to explain about Bronsted-Lowry theory. According to the diagram shown, we can note about how the Bronsted-Lowry acid reaction going on. At the reactant part, we have acid and base, while at the product, we have conjugate base and conjugate acid. A Bronsted-Lowry acid is any species that is capable of donating a proton H+, while a Bronsted-Lowry base is any species that is capable of accepting a proton but must have at least one lone pair of electrons to form a new bond with a proton. Bronsted-Lowry theory, also known as proton theory of acid and base. These theories are introduced independently in years 1923 by Danish chemist Johannes Nicholas Bronsted and the English chemist Thomas Martin Lowry, stating that any compound that can transfer a proton to any other compound is an acid, and the compound that accepts the proton is a base. A proton is a nucleus particle with a unique positive electrical charge. It is represented by the symbol H+ because it constitutes the nucleus of the hydrogen atom. Let's go through about how electron transfer in the Bronsted-Lowry theory. As the example given in the slide, we can see that the reaction between H2O and NH3. In the reaction, water, which is H2O, is an acid, while the ammonia, which is NH3, is a base. Because the water lose one proton in the reaction, and the NH3 gained one proton in the reaction. Okay. In the slide, we can see that H2O loses a proton, H+, and forms OH negative, which is conjugate base, while NH3 accepts a proton to form NH4+, which is known as conjugate acid. As we know that the molecule of ion that's formed when the acid loses its proton is called the conjugate base of that acid. And the molecule of ions that forms when the base accepts a proton is called the conjugate acid. Then I'll pass to Ibrahim.
Okay, thank you, FB. Can you hear me, guys?
Yes, can.
Okay. Can see my screen?
Yes, we can. Yes.
Okay. So let me just open the webcam. Okay. Okay, we're gonna talk about Lewis definition of acid and base. Okay. So a Lewis acid is a substance that can be accept a pair of electrons, as a Lewis base is a substance that can donate a pair of electrons. So we explain it about what's the acid and base. Okay, in organic transformation, the creation of products from reactions essentially results from a process of breaking bonds and forming new ones. This process basically amounts to electrons pair transfers. Ionic mechanisms involve electron pairs transfer and are therefore described by the Lewis acid base theory. Okay, the Lewis definition implies the presence of high electron density centers in Lewis bases and low electrons density centers in the Lewis acid. In a reaction between a Lewis acid and a Lewis base, the electrons pairs donated by the base is used to form a new sigma bonds to the electron deficient center in the acid. Okay, the identification of Lewis base follows basically the same guidelines as the identification of the bronze bases. They frequently contain atoms that have non-bonding electrons or lone pair. On the other hand, Lewis acid frequently contain atoms with the N incomplete octet, a full positive charge or a partial positive charge. Okay, we take some common Lewis acid and base as we see in Lewis acids: proton, boron, trifluoride, ammonia chloride, and carbon dioxide. And Lewis base: hydroxide ion, ammonia, carbon monoxide, and water. Okay, we take an example about hydroxide ion. So HO minus is a Lewis base because it donates a pair of electrons, and H plus, the proton, is Lewis acid since it accepts a pair of electron. We take another example by detail. Okay, we can see here reaction between ammonia and boron trifluoride. As we can say, unhybridized 2p orbital of boron atom, okay, in boron trifluoride accept, okay, the electron pair from ammonia, okay. Thus, in this reaction, ammonia is a Lewis base and boron trifluoride is a Lewis acid, although no proton transfer in the observed here. Okay, we go to another example. So we talk about water, which is important for us. Okay, water is a carbocation or example for a Lewis acid. When water reacts with a carbocation as shown below, one of the electron pairs, okay, from oxygen is used to form a new sigma, okay, form a new sigma bond to the central carbon in the carbocation. As with Bronsted acid base reactions, curve arrow are used to indicate the movement of electron pairs during the reaction process. The arrow always originate with the Lewis base, okay, and moves toward to area of electron deficiency in the Lewis acid. Okay, attention, this is very important for us to recognize between Lewis acid and Bronsted acid theory. Okay, to avoid confusion between the Lewis and Bronsted definition of acids and bases, Lewis bases are sometimes called nucleophiles, and Lewis acids are called electrophiles, as we have seen in the example of water. Okay, it acts as a nucleophile, donates electrons, and carbocation acts as a nucleophile, receive electrons. Since Bronsted acid and base are a subcategory of the more encompassing Lewis definition, it can be said that most Bronsted bases are also nucleophiles, and that the proton is a Lewis acid or an electrophile. So there are, however, some subtle differences to keep in mind, and thank you for hearing. Okay, guys, you can who is the next?
I'm the next.
Okay,
Okay.
thank you.
Share.
So I'll I will talk about heterolysis and homolysis. So what is heterolysis all about is it's actually a breakage of single bond with two electrons distributed unequally between two atoms bounded by the bond. So this bond breakage between carbon atom and living group will lead to two formation of ions. So we will see next what kind of ion it will form. So as I said, heterolysis, whenever a molecule undergo heterolysis, these two atoms bonded together will the bond breakage will distributed two electron unequally. This double-headed arrow indicate the two electron distributed into this B atom, so that it results in A become carbon anion and B carbon cation, and B become carbon anion. So two form of ion that will form after undergo heterolysis is first carbocation. Carbocation we can say as electron deficient. Electron deficient means it has less electron, make the atom become positively charged. We can also say it as Lewis acid as it electropair acceptor. So means when this atom undergo chemical reaction, it will looking for more electron to make it stable. So this is the example how it going. This bond breakage into a bromine atom, leaving this make this bromine atom become negatively charged, and this is the Lewis acid positively charged. So next kind of ion is carbon anion, which is electron rich. Mean it has a lot of electron make it become negatively charged. So in this case, the both electron will be distributed on this A atom, make it become negatively charged. So this is the example, and we also can say is Lewis base because it will donor the electron pair. So mean when these molecules undergo chemical reaction, this lone pair will be donated and become a bond. So we look about homolysis. So homolysis is also breakage of single bond, but this time these two electrons distributed equally between two atoms. So as you can see here, it distributed equally, make this atom become free radical, and it's stable because it doesn't have ion or charge. So if you want to draw the mechanism, we should use the a half-headed arrow. This half-headed arrow represents one atom, one electron distributed on each of these atoms. So it will become this. As you can see here, this is the example. So next we will talk about the electrophile and nucleophile. So what is electrophile? Electrophile is actually electron loving, which means it love electron as it is less of electron, or we can say it electron deficient. So electrophile usually it positively charged or partial positively charged. So when it electron deficient, when it undergo chemical reaction, it will looking for some electron from elsewhere. So this is the example. This is a polarizable pi bond because this is as we know, carbon atom is positively charged, partial positive, and oxygen atom is partial negative. So it become polar molecules here, and this is negatively charged. And one important thing we should know about electrophile is electrophile will accept electron in chemical reaction because it electron deficient. So next is nucleophile. Nucleophile. Nucleophile is nucleus living, which means it have a lot of electron. So it will tend to donate the lone pair or electron pair to form a new bond. So this is the example of nucleophile. It may have a negatively charged or lone pair here. So the important thing we need to know about nucleophile is it will provide electron for making of new bond. So typical example of electrophiles and nucleophiles. So we look into electrophiles first. First, this electrophile usually have living groups. As we can see here, this is living group because when this bond breakage here, this alkyl group tend to become positive, means it will become electrophiles. And this is a molecule with carbon double bonded to O. This is what I mean by polarized pi bond. So next we look into nucleophiles. First, we choose a nucleophile must be negatively charged and not bulky. The reason why it's not bulky because it will make it easier to attack molecules when undergo chemical reaction. And the nucleophiles also molecules with neutral N, P, and or S here. So for electrophile and nucleophile, it have two kind of reaction, which is one bond breaking reaction and next is reaction without bond breaking. So first, for reaction with bond breaking, first we have to identify which bond were made and which bond are broken. So as we can compare oxygen atom and bromine atom here, bromine atom is more electronegative, so it tend to broke here. Then we need to identify which is electrophile and which is nucleophile. So as we know, nucleophile have a negatively charged, so this will become the nucleophile, and this this molecule have a living group, right? So it will become electrophile. So when this bond broke, this nucleophile will attack this carbon, and they will form a new bond here, and the bromine atom become negatively charged. So next reaction without bond breaking is first we have to identify which is partial positive and which is partial negative. So for partial positive, it will become electrophile, and this is partial negative become nucleophile. So to draw the mechanism, we have to draw double-headed arrow, which means this lone pair will attack this partial positive carbon and become positively charged molecule here, and this living group will become negatively charged. So that's all from me. I pass to Hakim.
Kimin tak dengar.
Hello.
Dengar.
Hello, my name is Muhammad Hakim bin Zadali from Group 4, and now we'll talk about the proton transfer mechanism. So first, I will get back for the roasted lauric acid and roasted lauric base. As mentioned, the roasted lauric acid is a species that can donate a proton, while roasted lauric base is the species that can accept proton. So roasted lauric acid must contain a hydrogen that can be dissociated as a hydrogen ion, while a roasted lauric base must have at least one lone pair of electrons in order to form a new bond with the proton that is donated from the prostanoic acid. So now we'll go to the example. So this is a reaction between ammonia and water. The chemical reaction does not go to completion rather than the reverse process occur, as well as, and eventually the two processes cancel out any additional change. At this point, we say that the chemical reaction is at equilibrium. Both processes still occur, but any net change by one process is counted by the same net change by the process. It is dynamic rather than static. Because both reactions are occurring, it makes sense to use a double arrow instead of a single arrow. The NH4 ion is donating a proton to the hydrogen ion, which is accepting it. This means that the ammonium ion is acting as the proton donor of roasted lauric acid, while the hydrogen ion, the proton acceptor, is acting as a roasted lauric base. The reverse reaction is also a Bronsted lauric acid base reaction. The two sets, which is the ammonia and ammonia and water and hydrogen ion, are called conjugate base and acid. We can say that the ammonium ion is the conjugate acid, while the hydrogen ion is the conjugate base of the water. So I think that's all from me.
Okay, you can see my screen and hear my voice, right, guys? Can you?
Yes.
Okay. Okay, so thank you to Phoebe, Ibrahim, Hazika, and Hakimin for presenting their parts just now. My name is Devanandini, and I will be covering on acid strength. Okay. So what I will be covering on in acid strength is the definition theory part, and also the Ka and pKa values relationship with acid strength, and also the factors that affect acid strength. Okay. So what is acid strength? Acid strength is the tendency of an acid to donate a proton. So if an acid is more ready to donate a proton, the acid is actually a stronger acid. Okay, a strong acid that readily donates a proton will form a weak conjugate base, and a strong base that readily accepts a proton will form a weak conjugate acid. So as you can see here, there is an inverse relationship that exists between the acidity and basicity, right? Because like I said, strong acid will form a weak conjugate base, and strong base will form a weak conjugate acid. So you can see it's an inverse relationship there. And also Ka and pKa values, they have a lot of importance to determine the acid strength. So I'm going to explain on that part now. So if you see here, there's an equation here that I've put. So you can see AH, then there's this double arrow. It means that it is a reversible reaction, forming an anion here plus a proton. Okay, this is a hydrogen ion. So as we all know that strong acid will completely dissociate in water, right? And a weak acid will only partially dissociate. So it's the same case here. When an acid dissociates, it will release a proton, which is this hydrogen ion, to make the solution more acidic. But weak acids, on the other hand, they have both the dissociated state here, the anion, and also the dissociated state, which is the reactant, that will coexist according to the following dissociation equilibrium equation. So this is the equation, and this Ka, it stands for the acid dissociation constant. And if we look into this equation, the square brackets here, which has the anion, the proton, and also the reactant here, the square brackets actually indicate the concentration of each of the respective component. And based on this equation, the Ka expresses how easily the acid can release a proton. The equation also shows how the dissociation state of weak acid is different according to the proton level in the solution. So but then, like, if you look into weak acid, the Ka value is usually long. It's a very long number. So that's why here I put that the expressing acidity in terms of the Ka constant alone can be very convenient. So this is why the pKa was introduced as an index to express the acidity of weak acid. So for example, we take acetic acid. Acetic acid is considered a weak acid. So the Ka constant for acetic acid is 0.0000158. It's a very long number, right? So that is why the pKa constant is introduced. So it gives a simpler expression. And this is the formula to calculate the pKa value, which is negative log 10 multiply with the Ka value. And how does this Ka and pKa value actually relates to the acidity strength? Okay, for example, we take here the hydrogen iodide, right? Is the strongest acid. So if you see here, the Ka value is the largest if you compare to the Ka values of all the other acids here. And if you look at the pKa value, the pKa value of hydrogen iodide is the smallest if you compare to all the other values of the pKa values of the other acids. So from here we can see that the Ka value is the largest and the pKa value is the lowest for the strongest acid. So we can conclude that if the Ka constant value is higher, the pKa value is lower. So it means that the acid is stronger. So it works the opposite way for the weaker acid. So the Ka value will be smaller and the pKa value will be higher. So it means that it's a weaker acid. Also, another important thing is that organic acids are usually weaker than inorganic acids. So if you see methane here, it's actually an organic acid. That's why it's considered a weak acid. And hydrogen iodide here is an inorganic acid. So that's why it's considered a stronger acid. Okay, so this is how the Ka and pKa values relate to the acidity strength. Next, we'll look into the factors that affect acid strength. If we look into our lecture notes, there are only 4 factors, but they're actually more or less the same. The only extra one here is the charge. Then there's the role of atom, which is the same as the notes. I think in the notes is the element effect. Yeah, then there's resonance, inductive effect, and also orbitals. Orbitals also means the hybridization effect. Okay, so we look into the first factor, which is charge. So removal of a proton will decrease the formal charge on an atom or molecule by 1 unit. So if you look here, the acidity will increase with the increasing positive charge on an atom. We have 3 components here. We have a hydroxide ion, then we have water, and we have hydronium ion. And this hydroxide ion, it has a negative charge. The water here, H2O, has a neutral charge, and the hydronium ion here has a positive charge. So if you see, the pKa value of the hydronium ion with the positive charge is the lowest. So we can say that the acidity of this component, hydronium ion, is the highest. So when the positive charge on the atom increase, the acidity increase. So it works the same way for this second example. For NH2, NH3, and NH4, NH2 has a negative charge, and then NH3 is neutral, and NH4 has a positive charge. So the pKa value for the one with the positive charge is lower, so it means the acidity strength is higher. Okay, next we'll look into the role of atom, which is also known as the element effect. So if you look into the periodic table, when it goes across the periodic table, we know that the electronegativity increase, right? Because like for example, we take this example here. We have methane, ammonia, water, and hydrogen fluoride. So we look into the component carbon for methane, nitrogen for ammonia, oxygen for water, and fluorine for hydrogen fluoride. So you can see that the electronegativity of fluorine is the highest. It has a value of 4, and for carbon is the lowest. So the pKa value will be decreasing according to the increasing electronegativity. So that is why we say that the acidity increase with electronegativity across the periodic table. But then it doesn't work the same way if you go down the periodic table, because we will look into the size factor. For example, we take the example of hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. So the fluorine here has an electronegativity of 4, chlorine 3, bromine 2.8, and iodine 2.5. So supposedly we have to like here I said we have to follow the electronegativity, but it doesn't work the same way for this, because we have to look at the size. So if you see here, the ionic radius of hydrogen fluoride is the smallest and hydrogen iodide is the biggest. So if you look into the pKa value, the pKa value of hydrogen iodide is the lowest, so it means that the hydrogen iodide is the strongest acid here. So the first reason why the hydrogen fluoride is not considered a strong acid as compared to hydrogen iodide is because because of the shorter and stronger HF bond as compared to the other larger hydrogen halides here. The second reason is because of the stability of the conjugate base. The fluoride ion here with the smallest ionic radius will only bear a single negative charge, so it is spread over a smaller volume if compared to those of the larger halides here, so it is energetically unfavorable. So that is why hydrogen iodide is considered the stronger acid. Okay, the next factor is resonance. So as we all know, a huge stabilizing factor for a conjugate base is if the negative charge can be delocalized through resonance. So here I have an example of methanol and phenol here. And if you look into the pKa value, phenol has a smaller pKa value, so it makes it more acidic than methanol. This is because when you draw the resonance structure, the anion of phenol here can be stabilized through resonance. Okay, so that is why it is more acidic. And the second example here, we have methanol and also carboxylic acid. So the pKa value of carboxylic acid is lower than the methanol here, so it works the same way. You draw the resonance structure, so the anion here can be stabilized through resonance. So that is why carboxylic acid is considered the stronger acid. Okay. The next factor is inductive effect. So we know here that there are two principles to look into. The electron withdrawing substituent can increase acidity of a nearby atom, which will increase with electronegativity and decrease with increasing distance to the atom. So we can see here that the electronegativity increase in order. Fluorine has the highest electronegativity, with iodine having the lowest. So if you look into the pKa value, the component with the fluorine has the lowest pKa value, so it is the most acidic. So if you look into the second example here, the distance between the electronegative element, which is the bromine here, with the negative charge is quite far if you compare with the second component and the third component here. The distance of the first electronegative element with the negative charge is further away, so that is why it is not considered a strong acid. So if the distance between the electronegative element and the negative charge is nearer, it means that the acidity is stronger. So that is why if you want to conclude it, you can look at the pKa value. This third component here has the lowest pKa value, which makes it a stronger acid. And the last factor here is orbitals, also known as hybridization effect. So again, the acidity relates to the stability of conjugate base. So if you look here, when we have a more percent of the S character in the orbital, the electrons will be closer to the nucleus, so the energy will be lower, which makes it stable. So if you look into the first component here, the carbon here has a sp3 orbital because it has 3 hydrogen bonds and 1 bond with carbon, so makes it there are 4 bonds. So if 100 divided by 4, we have 25. So it has a 25% S character. If we look into this second component, the carbon here has 3 bonds, one with hydrogen, one with carbon, and a double bond with another carbon. So 100 divided by 3, you'll get 33% of S character. And the last one here, the last component here, carbon has 2 bonds, one with hydrogen and one triple bond with a carbon. So 100 divided by 2 will get 50% of S character. So as the percent of the S character increase, the electrons will be closer to the nucleus, right? So it's lower in energy, so it's more stable, so the acid is a stronger acid. So the one with the more S character is has the highest acidity. So I have something simple for you guys to remember the factors. So we have 5 factors here, right? Charge, atom, resonance, dipole, induction, and orbital. So we take the first letter of each of the factors. So we'll have cardio. So I think it's a simpler way to remember the factors that affect the acidity strength. So I think we have come to the end of our YouTube live session. Yeah, so do you guys have any question to ask? Yeah, I'll wait for a while. If there's any question, you can ask. If you're not clear about anything, yeah, I think there's no one asking questions here. So yeah, so thank you everyone for watching our presentation session, for giving your time and attention. Thank you to everyone who presented as well.
Thank you.
So should we end? There's no one asking anything.
Yeah, I think we should end now.
Yeah, okay. So, okay, thank you everyone again for watching. Have a good day. Stay safe. Bye. Oh, and don't
Thank you,
forget to like.
guys. Thank you. Bye-bye.
Okay, bye-bye. Thank you.
Right.